All right, today we're talking about behavior of polynomials, kind of their intro to graphing polynomials. So a lot of this, yes, we can get by just graphing with the graphing calculator, but it's important to understand parts of our graph and what we can get from our equation. So I've loaded in an example over here, and there's a couple key parts that we'll want to look at today. So the first one is called the degree, which we've already looked at, right, when we were naming things. This is the degree of our polynomial. And a degree 3 polynomial tells us we have 3 solutions total. They could be real, they could be imaginary. And it also means we cross the x-axis up to 3 total times. Okay, so we could maximum number of times we cross the x-axis would be 3 times. It might be less than that. We'll see. Okay, next up we have the leading coefficient. So in front of my highest degree term, which was x to the third, the coefficient or number in front is called our leading coefficient. And what that tells us is whether or not the right-hand side of my graph is going up or down. Okay, so if this is positive, the right-hand side of my graph will rise, and if it's negative, it will fall. It will go down on the right-hand side. So the very right-hand side of my graph, the sign of my leading coefficient, whether it's positive or negative, will tell us which way it's going. And lastly, from our equation, we can look at the very end. And the constant at the end, okay, when our polynomial is in standard form, is our y-intercept, where my graph crosses the vertical axis, the y-axis. Okay, so we actually know a lot of stuff about this graph. Okay, so to reiterate what we talked about here, the leading coefficient describes the very end behavior, so as we go very far to the right-hand side of my graph. Okay, specifically, if it is a positive number, if my leading coefficient is positive, the right-hand side of my graph will go up. Okay, I don't know what's happening on the left. It could be, going down. It might also be going up. I don't know, but I know the right-hand side, okay, is going up. So one of the ways we notate this is called limit notation. This says as x approaches positive infinity. So think about our graph where our positive numbers go to the right and up. So as x, the horizontal, goes towards positive infinity as we go to the right on our graph. That's what this is describing. F of x, which is y, my function, is going up. It approaches positive infinity, so we're going up towards the positive numbers. So as x goes to the right, y goes up. As we go to the right on my graph is going up. It's kind of what this describes. Okay, so we've worded that down here. Okay, if I get a negative leading coefficient, we know the right side is falling. Okay, again, I don't know what's happening on the left side necessarily yet. It might be rising. It might also be falling. Okay, but I know the right-hand side is definitely falling. Okay, so the right-hand side is definitely going down. And this says as we go right on my graph, my function is going down towards negative infinity, right? So as we go to the right, my graph is going towards the negative numbers. It's going down on the right. Okay, again, the degree, which we talked about back up here in blue, tells us how the left and right end behave when we compare to each other. Okay, specifically, if I have an even degree function, so if it's degree 2, or degree 0, or degree 4, or 6, or 8, any number, if the highest power is even, the left and right hand side will go the same direction. So think about, for instance, x squared, right? We had parabolas that opened up or opened down, but they were either both going up or both going down. The left and right behaved in the same way. That's true about x to the 4th, x to the 6th. They're either both going up, the left and right hand sides, or both going down. There could be all kinds of crazy stuff happening in the middle, but I know at the extreme left and right, all even degree polynomials either both go up or both go down. If it's an odd degree, like the one we had above, the left and right side will go in opposite directions. So if it's an odd degree, say x cubed, one might be going up and the other is going down, or vice versa. Maybe the left side is going up and the right side is going down. Okay, so it could kind of be either case for these. There might be all kinds of weird squiggles and things happening in the middle, but I can tell you what's happening at the extreme ends. They're going up or down. Odd degree functions always go in opposite directions. Even degrees always go the same direction. And remember, we can basically figure out which direction by looking at the leading coefficient. If I know what's happening with the right, and then I know the left is doing the same thing, hey, I can figure out what both sides are doing. Or if I know what's going on the right, and I know they go in opposite directions, we can figure out what the left is doing as well, right, with a little bit of deduction. Okay, so let's use these ideas. It says describe and sketch sketch the end behavior and identify the y-intercept. So let's look at first our degree. This is an odd degree function. And that tells me my tail ends go in opposite directions. So if the right's going up, the left's going down, etc. So they go in opposite directions. And then we're going to look at our leading coefficient, which is -2. And that tells me the right side, specifically, goes down. Oops, that's supposed to be a W, down. Okay, so if I know the right side's going down, and they go in opposite directions, well, then the left side needs to be going up, right? So the left side would need to be going up. So the left side goes up, the right side goes down. Right side goes down again because that's negative, and they go in opposite directions because it's odd. So there is our sketch for end behavior. Then it wants me to identify our y-intercept. And so we do have a nice constant at the end. So my y-intercept is the point 0, -5. Okay, let's try our next one. B. And again, we can kind of look at the degree and leading coefficients. So here's my highest degree, which is even. Remember from the previous slide, even degrees go the same direction. So these go the same direction. They're either both going up or both going down. Okay, then we can look at our leading coefficient. In this case, we have a hidden +1. The +1 says our right side goes up because it's positive. So we're just looking at the sign there. The right side goes up. So if the right side's going up and they go in the same direction, then the left side must also be going up. And again, I'm not exactly sure what's happening in the middle, but I know it's smooth and continuous and there's nice curves, but I know the left and right side are definitely both going up for that graph. And so here is my y-intercept. Ooh, notice there is no constant. And if we're missing a constant, we can think of it as being 0. This graph goes through the origin, 0, 0. That's where we'd write our y-intercept. Okay, our next one. This one, try these next two out, I would say, actually. So pause the video now, see if you can figure out roughly what directions they're going in and what our y-intercept is for C and D. All right, here we go. For C, you should have come up with they go in opposite directions. It is an odd degree function. My leading coefficient was positive, so the right side went up. And since they go in opposite directions, the left side must be going down. We also did have a constant, +4, so my y-intercept is 0, +4. For D, should have come up with they go in the same direction and that the right side goes down. So if the right side goes down and they go in the same direction, they're both going down. Okay, my y-intercept here, we did have a constant of -1, so 0, -1. Okay, again, these can all be checked with Desmos just to show, right, what's happening on the left and right-hand side by just graphing them as well. The next thing we're going to talk about is what's called the multiplicity. Okay, multiplicity is the number of times an x-intercept, also called a root or 0, is repeated. So let's say if we're solving something and we get the answer 2 twice, that would mean we have a multiplicity of 2 because it's repeated twice. It's the number of times an answer is repeated, essentially. Okay, so a couple odd things that happen here, I guess pun intended. If it's an odd multiplicity, so it repeats itself or it's we get that answer back 1 time or 3 times or 5 times, my graph will cross the x-axis. So if this is the x-axis, okay, if this is our x and y axis, an odd multiplicity in my graph might just pass through. Okay, it's just passing on through. It's just going to cross the x-axis at whatever that value is. Okay, however, if we get an even multiplicity, my graph actually bounces off the x-axis. It does not pass through to the other side. Okay, so if we had a graph with an even multiplicity at this value, say -1 or -2, whatever that would be, it might come from the top or bottom and it kind of hits that point and turns around. Like it doesn't pass through to the other side. Okay, so anytime it's repeated an even number of times, we'll see it kind of deflect off or bounce off the x-axis. It will stay on the same side. Okay, so we have 2 kind of big examples. I know this is a lot here, where we're going to try to find all of the zeros through factoring. We're going to use multiplicity and end behavior to sketch a graph. Okay, first thing, let's figure out what's going on with my end behavior here. So this is an even degree, which means the tail ends go the same direction. My leading coefficient out here is a +1, which means the right side goes up. Okay, so roughly, I know if the right side's going up and they go the same direction, you know, who knows what's going on in the middle, but I know the left and right side should each be going up so far, just by looking at my equation. We can also find our y-intercept. Here there is no constant, so I can say that my y-intercept is 0, 0. This graph actually goes through the origin, and we can put that point on our graph. That is definitely a point on our graph, 0, 0. Okay, to find all zeros, we actually take our equation, x to the 4th minus 16x squared, and we'd set it equal to 0. Then, because we're factoring, we'd want to look for a greatest common factor, and all terms on this side have at least x squared. So if we divide an x squared out of each of those, that leaves me with x squared minus 16. Okay, the factor inside of our parentheses is a difference of squares. This actually does factor out further. The 2 numbers that multiply to -16 and add up to 0 for the missing middle term, it's x plus 4 and x minus 4. And now if we set each factor equal to 0, either x squared equals 0, or x plus 4 equals 0, or x minus 4 equals 0. So for this first one, if you square root both sides, don't forget we have to put plus or minus, or that this actually tells you there are going to be 2 solutions. We get plus or minus 0, or in other words, we get 0 twice. So this is just a comma, we're just listing our values. Here, if we subtract 4, we're going to get x equals -4. It's one of our solutions. And here, if we add 4, we're going to get +4 as another solution. Okay, so the fundamental theorem of algebra tells us this has 4 solutions, real or imaginary, and they all end up being real values. So we're going to list our zeros, aka x-intercepts or solutions, the things we just found here, and how many times they're repeated, their multiplicity. So I like to start with the smallest number, which would be -4, and that only occurs 1 time, so its multiplicity is 1. The next smallest number would be 0, which occurred twice. It has an even multiplicity. And our last one would be +4, which only occurs once. So here's how we're going to use this to roughly sketch a graph. I know my graph is going to cross the x-axis at -4, 0, which we've already graphed, and +4. So it's going to at least touch the x-axis at those points. It might bounce off or it might pass through, depending on if our multiplicity is even or odd. So I'm also going to come back to my rough sketch. I know the right-hand side here is, or sorry, from the left-hand side, it's coming from above. So I can begin somewhere above, and I'm going to start to come in towards -4. Okay, so I look at -4, and its multiplicity is 1. That's an odd number, and that tells me that we're just going to cross the x-axis at that value. So we come in, we just cross at -4, and eventually we're going to start curving back up towards 0. Nice smooth curve. Maybe make that a little nicer. Okay, and as I head towards 0, I notice it has an even multiplicity, right? We got 0 twice from that x squared term. And if it's even, it's not going to pass through. It's going to bounce off my x-axis. Bing! Just bounces right off. Stays on the same side. And then we go down a ways, however far you want. We slowly start coming back up towards 4. And 4 only occurs one time. And in odd multiplicity, it just passes on through. So this graph will just continue to come on through, and it will continue upwards, kind of like our sketch here that we knew the left and right side was going upwards. We didn't know exactly what was going on in the middle, but finding our zeros and their multiplicity gave us a pretty good idea. Okay, here's a sketch of this exact graph through Desmos. We can see things like where it's crossing the x-axis or bouncing off the x-axis at 0. It's passing through at -4 and passing through at +4. Now it does, of course, on this graph you can see it goes way lower than we did in our hand sketch. Don't worry about that. The correct things we're looking for is that it looks like it's rising on the left and right. It is a very steep one. That it's crossing at +4 and -4 and bouncing off at 0 and staying underneath. And it's roughly doing those same things in here. Obviously, yes, it was much more steep than the realistic graph, but this is good enough for a hand sketch graph. All right, let's do our last example here. So we're asked to find all zeros, okay? Use our multiplicity and behavior to sketch a graph again. So first thing we look at is our degree. This is an odd degree function, which tells me the tail ends go in opposite directions. Tail ends go in opposite directions. Okay, next we would look at the leading coefficient, which is -1, and that describes the right-hand side. So the right side goes down or is falling. Okay, so I know a little bit about my graph so far. I know the right side goes down, and my tail ends go in opposite directions, which means the left-hand side has to be going up. Next, we can look for our y-intercept. There is no constant, so my y-intercept would be 0, 0. Similar to the last graph, this goes through the origin. Okay, to find my other x-intercepts, we need to take our function and set it equal to 0. Okay, so here's my function, set equal to 0. The first thing we look for when we're factoring is a greatest common factor. And I see I can take out at least an x squared from every. Okay, so we factored out our x squared. But if I'm going to try grouping, generally I would like this first term to be positive. So I'm actually going to divide out a -1 and bring that out front in my next step here. Okay, so it would look something like this. Taking out the -1 just changes all the signs in the parentheses. And we do have 4 terms, so we're going to try factoring by grouping. So in this first pair, I can take out an x squared, which leaves me with x plus 4. And in the second group, I can take out a -16, which would leave me with x plus 4. And remember, if factoring by grouping works, what's left in the parentheses has to match, and it does. So x plus 4, the matching set of parentheses, is one of our factors, and the x squared minus 16 is the other. Okay, and then we have our -x squared we took out earlier. This is a difference of squares, which factors as x plus 4 times x minus 4. And then we still have the x plus 4 to the right of it, and it equals 0. So now we would set each of these equal to 0. Okay, so we set them each equal to 0. Remember, from this, we're going to get 2 solutions. You divide by 1 and take the square root. We're going to get 0 twice. Here, when I subtract 4, we're going to get x equals -4. Here, when I add 4, we're going to get +4. And over here, when I subtract 4, we get -4 again. Okay, so let's write our multiplicity and zeros in our chart here. So the smallest value we ran into is -4, and that actually occurs twice. We have an even multiplicity. Next, we have 0, which also occurred twice. And then we have +4, right? That just occurred one time. So my graph is going to touch the x-intercept at -4, +4, and 0. I know from the left-hand side for my sketch, we're coming in from above. So we're going to come in from above. We get to -4 this time. It has a multiplicity of 2. So this is bouncing off the x-intercept, or x-axis, I should say. We're slowly curving back towards 0, which also has an even multiplicity and bounces off. And when we get to positive 4, it has an odd multiplicity. It's the last time we'll finally get to pass through. And so it roughly matches our end behavior here. And let's take a look at the actual graph and see how we did. Here is our Desmos graph. And we can see it is a lot steeper than ours again, but don't worry about that. Our left side is coming in from above. It's bouncing off at -4. It's bouncing off at 0 and passing through at +4. We did a pretty good job for a hand sketch graph. Okay, we'll go over more examples, less complicated ones. I tried to put some tough ones in the video for you in class. But don't forget, our degree, whether it's odd or even, tells us if my tail ends are going in the same or opposite directions. The leading coefficient tells me what's happening specifically on the right-hand side. Our y-intercept is always the constant when we're in standard form. And to find what's going on in the middle, we need to find all of our zeros by factoring and setting things equal to 0. And then we can look at their multiplicity, how many times they're repeated, to figure out whether it's just going to bounce off the x-axis or pass through.